Hello dear, welcome back to my lecture. I just came from outside and wearing a mask, as you can see. I'm just now removing it. But as you know, situation is very serious. Our country witnessed 300,000 infection per day yesterday. So wherever you go, you put on your mask and try to be safe. And now let us come back to our lecture. You see, a little bit recap, right? So what we did in last lecture, we wanted to design a small neural network which will run to input XOR pattern. Okay, and we were just training it. This is one iteration, iteration after iteration, another iteration, another iteration, another iteration, and all these 4 iteration constitute one epoch, and we wanted to just train our parameter epoch after epoch. Say it was just like j earlier plus delta w j epoch, right, of that epoch. So next epoch, the w will be earlier plus this. So we were calculating all this, and we figure out that it is not easy, right? A lot of complex thing need to be done, right? So first you need to we calculated the randomly we selected w, and then we calculated output with, from because we need to go. That's why it is called feed forward, right? We need to go from inside, that is from input, right? We need to go in this direction. We know input and what would be the output. So with haphazardly chosen W parameters, we are getting some output, and we needed to calculate all the output of this neuron. Okay, Y3, Y4, and our activation function we used sigmoid, and we could actually calculate, right? And the most interesting and most important thing is once you calculate Y5, actual Y5, and then you calculate error, now your training start, and most important thing is to calculate error gradient. Okay, so you see error gradient is equals to the derivative of the activation function times error. So this is this is how we calculated, right? It's a small quantity minus 0.12, and then we were able to just upgrade the parameter associated with this neuron, because now we have error gradient. So how much this has contributed to the error, now I know. This has contributed, I know, and accordingly I am calculating delta, right? And it turns out that minus some value we have got, right? So basically, you see, some values are plus, some values are minus. So it is basically what it is calculating. It is gradient descent. So delta learning rule is nothing but gradient descent algorithm. Gradient descent algorithm. Okay. So gradient descent algorithm you are calculating, and you remember, right? Otherwise, lecture 7, 8 you can go through. It's a wonderful thing. We have already explained how to calculate gradient descent. Numerically, we are calculating here gradient descent algorithm, and you have the option. Mostly stochastic gradient descent algorithm is what we prefer. The reason I'm going to tell you now. Okay, so this once you calculate your error gradient here, you upgraded the weights here. Now you need to calculate again error gradient here, and that actually again it requires your uh, your activation functions derivative times this is gradient which incorporates the derivative of the activation function here. So you see, and we are using um, we are using sigmoid as an activation function, right? So whatever may be your wi x xi minus w0 x0, okay, summation of I equal to 1 to n, say for example, right? So whatever this value is, the output after activation will be lying between 0 and 1 because we are using sigmoid activation function. So that is important thing to note because we will refer this. So we are trying to analyze that how it affects our performance of the network, right? So you see, again, for this neuron you calculate error gradient. For this neuron you calculate error gradient, and then only you can actually make error weight correction, right? Of these. Okay, so that's what we did. Now you see, um, this was a little bit minus something 0.16 like that, and when you calculated delta 3, it becomes very small, right? This also becomes very small, and this is true for only one hidden layer. So if the layer is increased, so for example there is another layer, okay, where you have 6 7, okay, 6 7 two neurons, right? So this you need to calculate. So this for calculating this you require again an activation function is sigmoid. So again you differentiate sigmoid and then you multiply with this delta 3 with delta 5, and then this sigmoid function's derivative. So things will be 0.033, next time it will be 0.00 something, right? So this happens because you are using sigmoid function, which is always zero, lying between 0 and 1. We'll discuss that issue, and it is actually decreasing this. This is the observation you make here, right? And so, and decreasing the uh, weight correction values. You see, already 0.0014, 0.0014, plus 0.0014. All kind of thing is happening here, right? So what's the problem? The problem is when, say, I have a network, fully connected network like this, having a large number of hidden layers, and my classification task is just not like a simple XOR pattern learning task, but say, for example, task to recognize a cat, right? Now, let us see what is going to happen. Now, cat, we see cat, right? Through our vision, through our cerebral cortex, through our learning. From the childhood, we know that this is cat. But how computer visualize cat? Just try to see. For computer, everything is number. So cat, say I am taking a picture, dimension 64 cross 64, and cat will have, if it is grayscale image, then only one. Otherwise, there will be two more channel, right? RGB, say this is for R, so there will be another. We'll show this. Okay. R. So here also there will be lots of number. So stack, another stack. Okay. Or this is G, this is B, for example. Okay. So if it is RGB value, say 64 cross 64, we have taken, so three channels are there, RGB. So those are the computer representation of cat. Okay, so and eventually that turns out to be 12288. It's a large number, right? And if I want to use till a densely connected neural network, or it is called dense neural network, or fully connected network, that means where every neuron is connected with other neuron, right? Then what will happen? I will have to train this network with this kind of x equals to say x1, x2 up to xn, and what will be the dimension? 12288 cross 1. And since a lot of nonlinearity in the values are there, because there are a lot of shadow image processing related things, right? Special information, this, that. So those are all we'll discuss. They are all nonlinear. Okay, so I need a number of hidden layers so as to train my image of a cat. Say 100 such images of a cat. So every time I will have to um, train my network with cat. Similarly, say with dog, with means hare, or with some other. Okay, so all this I'll have to train cat 100 times. So and I will tell it is cat, cat, and this is say multiple output, right? Now, what is going to happen in this scenario? You see, when my um, hidden layer number are increased, and I am still using sigmoid function. So this is a sigmoid function asymptote at 0 and 1. You see, uh, isn't it? You all know. If you do not know, now know. Okay, and this is the derivative, because time and again for calculating error gradient, I'll have to calculate the derivative of the sigmoid function, right? And this shows the derivative. And you see, for a small range only, it gives, that means is activation value it can accommodate. Okay, what is the meaning of that? Meaning is that if you do not have such a large input, this is fine, because this is the operational zone. That is, you can get some gradient value here. Okay, so this is the gradient value. Okay, but up beyond this, gradient is 0. Beyond this, gradient is 0. And you can look here a little bit deeply. See, this is my for this neuron, this is error gradient I have calculated. And if I still want to run back propagation algorithm, conventional one, and use sigmoid function, then what is going to happen? You see, this neuron, I need to calculate again gradient, error gradient, right? That is differentiate the sigmoid function. So in the chain rule, this will be something like dot dot dot. So as many hidden layers are there, that many gradient, error gradient are to be multiplied to get error gradient in the beginning layer, right? Say this is beginning, and all these are because we are using sigmoid function, value slide between 0 and 1 fraction. Say this is 5, this is 0.3, 0.1, 0.2. So if you all multiply them, what is happening? Catastrophe is happening actually. 0.000 something. You just do it and you will get. So what does it mean? Means as you move in this direction, and you already know that okay, error gradient has to be multiplied to get the increment in W. So you won't be able to increment W, right? Because it will be negligible. And epoch after epoch, you will run and you will see that there is no appreciable change in weight. And you will be surprised, what happens to my algorithm? Is it running or not? It is running, everything is perfect, but we have done something wrong. What is that? We have used a wrong structure, okay, and we have used a wrong activation function. Now, some sort of remedy you can get if you change the activation function. Okay, like you see, this is called ReLU. This is another nonlinear activation function. Rectified linear unit, abbreviation is ReLU. The definition is that if x is negative, then it will return, the output will be 0, and if it is positive, the output, the it will pass whatever the input, output you will get same. This equals to this equals to this. Okay, x equals to f of x. Okay, so this is the characteristic function. So in applying ReLU, you are getting, you see, a there is no limitation that you will get only uh, uh, range of uh, activity of that changing W parameter is limited. No. Okay. So here your algorithm will run. Okay. However, still this is not a good idea to use a fully connected neural network for solving such a recognition problem where the data are unstructured. Okay, like this. Why? Because the moment you are trying to represent cat here or dog or whatever, right? So you have a 1 2 2 8 8 cross 1 vector, right? So this matrix you have inputted with this vector, and the moment you do, the um, subsequent layer, hidden layer, actually is trying to find the representation, right? It's trying to learn the important feature, but in this process, the spatial information is lost, isn't it? So 64 was the dimension, and now you have a single vector, the array with all these numbers. Okay. So losing that information is another bad thing for using fully connected layer for recognizing this thing, right? Apart from that, since the nonlinearity is induced in the hidden layer, uh, you won't have the luxury like your logistic regression, right? You won't be able to get this kind of objective function where you can make sure that your gradient descent is, when it is running, is giving you global optima. So here you will get local optima only. So you have to be careful, right? So what you can do, you can just minutely um, play around with alpha, which plays a very important role. So when you are actually sensing that you are trapping in local optima, then you can increase the value to jump from here. Okay, and when you are, but how to know that? It's very difficult, right? That's why we run stochastic gradient descent algorithm. Just sample out of so many W's, right? You sample some W's, okay, and then run gradient descent algorithm, so that to some extent the problem will be mitigated. However, though these are inherent problem, okay, that is losing information, using um, using your sigmoid function, gradient vanishes. By the way, it's called, the problem which you have witnessed is called vanishing gradient problem. Vanishing gradient problem. So it is clear, no? Why? What is vanishing gradient problem? Because when there are large number of hidden layer with fully connected neural network, the computation of error gradient is such that the chain rule multiplies the gradients which are between 0 and 1. So multiplying this fraction will further reduce the error gradient, and it will be negligibly small after some time, and you are using that error gradient to um, upgrade the W values, right? And W values won't be upgraded in the higher layer, which are nearer to the input layer. Okay, so that's an inherent problem. So those problems actually, together with local optima, so those problems made this fully connected neural network non-attractive. Okay, so in 90s and early 2000 also, neural network, stand-alone neural network, fully connected stand-alone neural network as a classifier actually did not look so promising, especially when other competitive tools were there, like support vector machine, decision tree, etc., etc. So that's the problem. Fully connected neural network. However, so in actually artificial intelligence, you see a lot of ups and downs. So with comparison content. Okay. So with introduction of convolution neural network, these problems actually were mitigated. Okay, and the idea that convolutional neural network can solve such recognition problem, which our fully connected neural network had, was proposed by in 1980s by Ian LeCun, and of course during that time computation power was not there. But 2012, Alex Nate, another graduate student, showed a postdoctoral student, showed that time is ripe to revisit deep learning and to reinvent, to redeploy the neural network in a new form, which is very, very interesting, and which I will just introduce here. And in the follow-up course of deep learning, you will start from here, convolutional neural network. But just briefly, let us see what it is and how it can solve or overcome the difficulties of fully connected neural network as a recognition tool in a standalone way. Okay, you need to remember stand-alone way. Okay, why this term I am using, it will be revealed just now. So now let us try to understand what convolution neural network is. You see, as you know, this is what I see is an image. Say this is image of an elephant, right? What computers see? Computers see three uh, RGB, three matrices. Okay, huge matrices depending on your structure of the input. Say 64 cross 64 is the image size into 3. There are 3 channels RGB. So each channel is a matrix which captures the pixel intensity value in that color. So computers see only 3 matrices with some numbers. Okay, and convolution neural network, which is the basic difference between fully connected and convolutional neural network, is actually here in the hidden layer. Neurons, all neurons are connected with all neurons? No. Okay, so neurons are actually connected with the filter, and they are trying to learn the feature by sliding the filter over the entire image, right? And I will discuss that. Okay, and after doing convolutional operation and associated operation with convolution operation, then actually what happens, the convolution operation, layer after layer, try to capture the features which earlier we were capturing somehow, right? So the algorithm is designed in such a way that the features automatically, layer after layer, are um, evaluated or determine what are the important features of, say, elephant. Or in that context, say I have a hand digit handwritten digit recognition problem, right? So again, Ian Lecon, together with other researchers, they developed the MNIST data set for handwritten um, digit recognition, and that's actually just like in formal language, you just first write uh, program hello world. This is hello world for data set is so important. It's hello world for machine learning researchers, right? So after all, later on, Facebook AI research actually upgraded it to QMNIST with more data and all, right? So what is here is happening, you see. So the convolution operation is actually able to extract feature, and then it is fed to a again fully connected layer, because now you have reduced number of data, okay, and it pass through a SubMax function, which mathematically actually is converts a vector number. So suppose I am trying to train my neural network with elephant, cat, dog, tiger, okay, some thousand elephant image, some different elephant image, and thousand cat image, uh, large number of tiger image, like that, okay. And my network is now trained. That means the parameters are now learned or fixed. Of course, the parameters here will be millions. So you see, we are now talking about millions of parameters and training and all kind of thing. In 1980s, it was not possible, right? We did not have GPUs. So now GPU can calculate all this. And then as a result of that, when you give, say, after training, successful training, you uh, get the output, okay, with a submax function value, which is telling you that elephant probability is 0.9. That the image now you have given as a testing, all right. Once it is learned, your system is learned, then it is giving 0.9 probability. Then cat, this is a cat, probability 0.03. It's a dog, 0.04. It's a tiger, 0.03. So again, sum equal to 1. So it is actually what is happening. Submax matrix, it's taking the numbers, it is giving some number, right, output. And when you are passing through the submax function, you are getting uh, a probability, a vector of probability, right? And this is how it is calculated for a particular output. Okay, submax particular output is calculated. All these probability values are calculated like this from some number. Okay, this is very useful actually function, and you will know how to write a submax function, and perhaps you already know. Okay, otherwise we'll tell you. So it's a very useful function actually, because it converts the score to a normalized probability distribution, and which can be displaced to a user. Say, um, subtly, after getting this display, I can see that this is a elephant, and if the values were not so nearer, for example 0.6, then also I can see what certainty my network is able to classify. Hmm. Same thing here. Say you have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So the neural network, convolutional neural network, will give you some numbers. Okay. And all these numbers, okay. So all these number when passed through the submax function will give you probability value, right? And then you can see probability of getting 8 is maximum, so you can infer that this max. That's how CNN works. And why CNN? Now you know, because fully connected neural network will fail to recognize such thing accurately because of the inherent problem I discussed. So with this, in the next class, we'll just introduce you how, what is a filter, what is a convolution operation, convolution filter, how it works, and how, as a whole, convolutional neural network can be a very useful recognition deep learning tool. And again, same neural network um, re-energized. Okay, so it was shadowed by other tools, that fully connected neural network, but standalone. But when it uh, it is clubbed with convolutional neural network, then again it is doing wonders. And this is the state of the art recognition tool nowadays. So stay tuned and we will discuss. So thank you. Stay safe. Bye bye.